thermodynamics, application of first law of thermodynamics in closed system as well as open system. Okay, in the previous section, we did look at so somebody is joining this class again. I thought everybody is joined already. Okay, so please let's hurry up. We don't have much time. Okay, so now proceed. Okay, so in this particular chapter, we'll be looking at the first law of thermodynamics, conservation of energy principle, heat transfer by work, mechanical forms of work, such as moving boundary, springs, shaft work, electrical work, paddle wheel, and then we'll look at closed systems. So the various, again, somebody is coming to the class. So I thought everybody is already present. Okay. Okay, so then we'll be looking at closed systems and then open systems. So open systems are the same as control volume systems, such as nozzle, diffusers, turbine, compressors, and so on and so forth. Okay, so basically the first law of thermodynamics, okay, is the law of conservation of energy. And simply it states that energy can neither be created nor destroyed, but it can be transformed from one state to another form. So, and this first law of thermodynamics forms the backbone of all engineering background. If you go to chemical engineering, you go to mechanical engineering, okay, even in physics, okay, in physical sciences, all of this, the application of thermodynamics is there. Okay, in every field of engineering that you can think of. So first law of thermodynamics is the law of conservation of energy, which simply says that energy cannot be created nor destroyed. It can only be transformed from one state to another. So in any thermodynamic system, okay, the first law of thermodynamics of any thermodynamic system is governed by this particular equation. So it simply tells us that the total amount of energy, let's say if we have a thermodynamic system like this, and some amount of energy is entering into the system, assuming it's a closed system, and some amount of energy is coming out. Okay, so let's say if we have 10 kilojoules of energy entering the thermodynamic system, and then 8, or let's say 2 kilojoules of energy goes out of the system. So eventually, there will be some amount of energy remaining in this thermodynamic system. And this is what we call the change in energy of the system. So the total energy in minus the total energy out should be equal to the change in energy of the system. Okay, so if we look at the physical meaning of thermodynamics, we will observe that if we put an object on top of a cliff or a mountain or a hill, okay, so as long as the object will be in stationary state, okay, there will be, so somebody wants to enter the class again. Yes, so like I was explaining, according to the first law of thermodynamics, the total energy possessed by that object on top of the hill is given by potential energy. What is potential energy? Potential energy is the energy possessed by a body by virtue of its position in the gravitational force field. You understand me? As long as an object is being held in the gravitational force field, then the energy possessed by that particular object is what we call potential energy. So at that point, the kinetic energy equals to 0 because the object has no velocity, it's not moving. But the moment you release the object, part of the potential energy will be transformed into kinetic energy. So you see, in this way, the energy is not lost. Part of the energy is being converted into kinetic energy, and therefore the object will start moving. Okay, so this situation is again related to the first law of thermodynamics. So now, if we look into this energy, the energy inlet, this E in minus E out. What is this E in and this E out? The E in and E out could be in various forms. Okay, there are three main types of the energy which can be transferred into or out of a thermodynamic system. Okay, so this, I think somebody again wants to enter the class. Okay, so yes, so there are three types of energy that are associated with a thermodynamic system. And this energy could be in the form of heat transfer, it could be in the form of work transfer, and it could be in the form of mass flow. You understand me? So, and then also we have three types of change of the energy of a system. It could be in terms of the internal energy, kinetic energy, and potential energy. So if you look into the original equation, sorry, I have to erase this for us to see. So, yes, so these energies, the E in and then the E out, are related to this. And the change in internal energy of a system could be also related to these energy changes. It means that if I have a thermodynamic system, okay, and heat is entering and some amount of heat is going out, there will be some delta E change. This is what we call change in internal energy. So the change in internal energy could be in the form of internal energy by virtue of its temperature. It could be in the form of kinetic energy by virtue of the motion of the object. It could be in terms of the potential energy by virtue of the position of the object in the gravitational force field. So these are the fundamental equations that governs the first law of thermodynamics. So if we break this equation into a more detailed form, then we're going to have the total amount of energy inlet can be written in the form of Q in, work input, and mass flow. So it means that we have a thermodynamic system in which there is heat transported to it, there is work transferred to it, and then there is mass flow. So an example, for example, could be a turbine. So we all know that a turbine is used to produce electrical power. At the expense of, it takes in some amount of steam. So the steam is coming in a form of mass flow. Mass flow, that is work. The mass is coming in, and by virtue of the mass that comes inside the turbine, some amount of work is being produced. We could also have W in. W in could be for a turbine. A turbine does not produce, sorry, a turbine does not consume electrical power. So there is no W in. Okay, so W in could be for related to a shaft. You have a thermodynamic system in which you have a paddle wheel or a shaft. So this is what is related to our W in. W in could be related to this. Whereas the heat transfer into this could be Q. You understand me? And then if you have the fluid flowing into this particular system, then that will be in the form of the mass transfer. Okay, so it is very important that we understand the basic fundamentals of this first law. Now, further, we can divide this equation. Again, this is the amount of energy that enters, amount of energy that goes out is this. So now, eventually, the delta E system, I've told you, it can be categorized in the form of delta U, which is the internal energy. What is internal energy? Internal energy is the energy of a fluid by virtue of its temperature. You understand me? If temperature increases, the internal energy of the system is going to increase in this way. And then we have the kinetic, and then finally the potential, the change, yes, change in potential energy, change in kinetic energy and internal energy. So if we rearrange this equation, so then we will have Q in minus Q out, delta Q in minus delta Q out. So then finally again we will have W in minus W out, and then mass in minus W out. This whole thing equals to the changing energy of the system. Okay, so now in a summary, this equation can be simplified in this form, that this delta Q in minus delta Q out is the same as delta Q. Okay, so sorry, change in Q minus change in Q out should be equal to delta Q in, sorry, delta Q, and then plus delta W plus delta M. This whole thing should be equal to the change in internal energy or change in energy of the system. So here we are saying that delta Q is nothing, it is this. Delta U is given by this, delta W is that, and then change in kinetic energy is this, change in potential energy, and then change in the mass flow is also given by this. So now we need to know the difference between this delta and then the change. See, so this is the change in, small change in Q in minus a small change in the Q out. There is a clear difference between this delta and this particular one, or the difference. So we normally refer to this, or we use this particular symbol when we are considering a path function. That is a situation where we have a path function means that, let's say, if we are considering a process in which there is a change in temperature. Okay, so temperature changes from, and we are transferring heat to a system in which the temperature changes from one state to another state. Okay, so the change in this temperature depends on the path through which the system passes. You understand me? And then also here we have a state variable or state function. State function is normally associated with the state property here. So for example, let's say if we have a graph like this, in which we have our thermodynamic system is undergoing a change of state, let's say from state 1 up to state 2, is undergoing an expansion. We have a fluid that is undergoing expansion, right? So at this particular point, the system could have a well-defined internal energy, say U1, and then well-defined internal energy, say U2. If you want to find a change in internal energy when the system is undergoing a change of state from state 1 to state 2, we have to use what we call delta U. You understand me? So this is what we refer to as state variable or a state function. Okay. So somebody again is entering the class. Okay. Yes, so over here we will have a situation like this where the state variables and then the part function are normally represented. Part functions are represented by this, and state variables are always represented by this. Now, when we take again, and when we say a part function, okay, part function means that the system or the change in variable or the property of the system depend on this particular path. Now, this delta U, it does not depend on the path through which the system goes. See, we could have also another thermodynamic system what is undergoing a change of state, but this time it is going through this route. So if it goes through this route, the delta U is going to be the same. Even though this is a longer distance, it is going to be the same. So this is what we call a state function or state variable. So the change in the property of the system depends only on these two states at the two end states. It doesn't depend on the path. You understand me? But if we talk about work, let's say the work done in moving from, let's say, this particular point up to state 2 depend on the path through which you take. If you take this through this route, this is a shortcut, and if you use this route, this is going to be a long distance. You understand me? So all part functions are normally represented by this notation. Okay, so and later on I'm going to explain to you in details and the relationship or the difference between these state variables, okay, or part function and then the state or point functions. Now let us look again at the definition of heat. What is the definition for heat? We say heat is the form of energy that is transferred between two systems or thermodynamic system and its surrounding by virtue of what? Temperature difference. So whenever there is a temperature difference between a system and then the surrounding, then energy is said to be transferred. Or we can say energy is the what do you call it? The transfer of heat from a higher temperature to a lower temperature of a system. You understand me? So then the heat energy can be in the various forms. So it could be in a form of, and we say that heat energy or thermal energy or simply heat is a form of energy transfer among particles or atoms in a substance, or maybe by means of kinetic energy of those particles. So these things are not so much of any importance. Okay, so important thing is that we should know that whenever there is energy transfer, then there is always a temperature gradient or temperature difference, okay, between the system and the surrounding. So the heat energy always refers to heat transfer of energy between two systems, not the energy contained within the system or the body. So if you have a body that has its own temperature, you cannot say that there is heat transfer, because there is no way heat can be transferred when the temperature of the system does not change. If the temperature is in equilibrium, thermal equilibrium, then there is no such thing as heat transfer or energy transfer. Now, if we look into this particular equation, heat is energy, while temperature is a measure of energy. This is justified from this particular equation. You understand me? So the word heat is a form of energy, which is denoted by this, while temperature is a measure of energy. Temperature is a measure of energy means that temperature tells us the degree at which a particular object, or let's say thermodynamic system, is being heated to. Okay, the degree of hotness or coldness of an object. Now, in thermodynamics equations, heat is a quantity of energy which may be transferred between the two systems, okay, which means that it's a part function or depends on the process of transferring the heat. Okay, so In thermodynamics, we have sign convention. Okay, so sign convention means that whenever you transfer heat into out of a system, or whenever heat is going out of a system, okay, so it is considered as a negative quantity. Okay, however, if heat is being transferred into a system, then it is a positive quantity, or a positive quantity is assigned to it. Okay, for example, let's say we have a system over here in which heat is being lost, okay, from the surrounding or from the system to the surrounding, and this is the Q out. This Q out can be represented in the negative sense, and if there is heat transfer to it, it is considered as positive quantity. You understand me? So these are the notations that we need to take note of. Okay, so then again we have specific heat transfer. Okay, so this specific heat transfer can be expressed in this form. So specific heat transfer is the rate of heat transfer per unit mass. See, heat transfer per unit mass is given by this. So it is kilojoules per kilogram. Just as we have specific enthalpy. Specific enthalpy is absolute enthalpy divided by mass. You understand me? Or specific volume. Specific volume equals to absolute volume per unit what? Mass. So the same thing applies to specific heat transfer. Is the absolute heat transfer per unit mass. Okay. So now the rate of heat transfer is always represented by Q dot. There is always a difference between Q dot and Q. Be careful, it's very important. So Q is the energy transfer and its units is in kilojoules. You understand? Whereas Q dot, this is the rate of heat transfer. It is kilojoules per second. Kilojoules per second, which is the same as kilowatt. So whenever you see Q dot, you have to be very careful. Okay, so in order to calculate this Q without dot, it is given by Q dot times time. So then you see, this is kilojoules per second, this is seconds. So if you multiply, you go back to the heat, what do you call it? The heat transfer. So now, if the heat is being transferred between two temperatures, sorry, between two time, let's say a time frame, let's say at time 1 up to time 2. So we can integrate the total amount of heat transfer, okay, starting from T1 up to T2, which is given by this equation. Okay, so now let's go a bit detailed about this particular energy or heat energy. Okay, the historical background on energy. So we have kinetic theory. So kinetic theory, we have already studied this in our, let's say, fundamental background, let's say either in your primary school level. So it simply says it's treat molecules as tiny balls that are in motion, and then they possess kinetic energy. Okay, so that's the background of the kinetic theory. So it means that if you take any particular object, okay, like the hot surface, it is made up of so many tiny molecules, and these tiny molecules have some energy stored within them, and by virtue of this, they are able to vibrate, they are able to move around. Okay, so because of the energy that they possess. Okay, so now we say heat is the energy associated with the random motion of atoms and molecules. So it means that the higher you subject an object to a higher temperature, more you subject an object to a higher temperature, then the more energy you store within that system. Now there are three fundamental types of heat transfer or heat transfer mechanisms. So in let's say in semester 5, where you will be doing thermal engineering, you will come across this very rich mathematics, conduction, convection, and radiation. You understand me? So conduction is the mode of energy transfer from a more energetic particles of a substance to adjacent less energetic ones as a result of what? Interaction between the particles. So if we look into this example, okay, so this is an object with a high temperature. So its particles are going to possess high energy, and this is an object with, at a lower temperature. So its particles will possess low temperature. So there will be potential to transfer energy from a high energy particles to a lower energy particle. And this phenomena is known as conduction. So you can see that conduction primarily occurs in solids. It could occur also in fluid as well. Okay, but at this level, let us say that conduction is strictly related to a solid situation. Okay, so conduction in the loose sense, it can also occur in fluids such as liquid, stationary liquid. You understand? So now we have convection is a mode of energy transfer when a fluid, okay, moves across a solid surface. So heat transfer or energy between a solid surface and the adjacent fluid that is in motion. It involves the combined effect of conduction and fluid motion, and this is what we call advection. So in thermal engineering, we will discuss all this in detail. You understand me? So all that you need to know is that, let's say if I have a flat plate like this, a flat plate, hot flat plate, if there is air flowing across it, we assume that there is air flowing across it, there will be energy transfer from the hot plate to the air. The mode of energy transfer is what we call convection heat transfer. So convection heat transfer takes place between the fluid which is the air, and then the solid surface. You understand me? So that's the convection. Whereas in conduction, it takes place between only two solid, between solid. You understand? So then we have radiation, the transfer of energy due to the emission of electromagnetic waves. Okay, so you see over here in this diagram, we have electric heater. This electric heater is emitting some amount of irradiation by means of, because of this hot surface, there is some electromagnetic waves or photons being emitted. And this phenomena is called radiation heat transfer. So now if we look into this diagram, the mode of heat transfer through this handle is conduction, because conduction takes place in solid, whereas convection takes place between liquid and solid surface. Okay, so these are the three main types of heat transfer as far as engineering is concerned. Okay, so now let us see the energy transfer by work. Now we are going to take them one after the other. So the energy transfer by work. Energy transfer by work can be in the form of shaft work, electrical work, spring work, or what you call the boundary work. You understand me? So these are the various forms of work transfer. Okay, so if we look into this diagram, yes, again, the sign convention for work is synonymous to heat. Whenever there is work done by a system, okay, so it means that it's a positive quantity, and then the work done on a system is a negative quantity. So it means if I have a piston cylinder, okay, I have a piston cylinder arrangement like this, in which there is work done by the system to the surrounding. So this is going to be work output, and this work output is going to be a positive quantity. On the other hand, if I have a piston cylinder, okay, arrangement where there is work done on the system, the work done on the system over here is going to be a negative quantity. Okay, so that's the sign convention part for work. Now, I've told that there are various or 4 different types of work. So the shaft work is that you place something like a paddle wheel in a fluid or in a substance. So as you rotate the paddle wheel, so the mechanical form of motion through the paddle wheel will be transferred to the fluid. So the molecules of the fluid will be agitated. There will be, again, there will be collision. More collision will take place. So the thermal energy of the fluid is going to increase. So we are transforming mechanical form of work through the paddle wheel into a thermal energy. So it means that the thermal or the thermal characteristics of the fluid or the substance is going to increase in this way. Then we have electrical work transfer. What is this electrical work transfer? So we connect electrical cable or a heater. So let's say in the morning you wake up, you want to perform some coffee or tea, then you put some water into this container, and then you put your electrical heater inside. So you connect it to electric source. You understand me? You connect this to electric source. So current will flow through it. So now there will be energy transferred. So the energy which is transferred into the fluid is called electrical work transfer. You understand me? So here again, we are converting electrical work into thermal energy. You understand me? So these are various forms of work transfer. Then again, we have the spring work. Spring work means here we have a piston which is loaded with a spring. So now this spring is exerting, the spring could be exerting some force on the piston. So it means it will push the piston to, again, to reduce the volume of the cylinder. So as it does that, it will be transferring some amount of work. Okay, so this work is what we call the spring work. And then lastly, we have the boundary work. Yes. So the boundary work is the work associated with this piston. So this is the boundary work. So as the piston moves between the cylinder, it will be performing some work. Either when the piston moves up, then it will be giving a positive boundary work, or if the piston moves down, then it will be giving a negative boundary work. Okay, so these are the different characteristics of the work that we have. So now let us see the difference between heat and work. So pay attention to this carefully. You could have questions on this, the difference between heat and work. So we have taken note that both are recognized at the boundary of a system as they cross the boundary. That is, both heat and work are boundary phenomena. Boundary phenomena means that, let's say if I have a piston cylinder arrangement like this, I have a piston cylinder arrangement. If I compress the piston, okay, I compress the piston, it means that I'm adding some work, W in, into the piston or into the cylinder. Those will be the W in. So it is crossing, the work is crossing the boundary of the system. Similarly, we could have heat transfer, which is also crossing the boundary of the system. So both work and heat are what we call a boundary phenomena. Okay, now system possesses energy but not heat or work. So we can never say that a thermodynamic system possesses heat or work, because what is the definition for heat? Heat is the transfer of energy from a higher temperature to a lower temperature. You understand? So the whole definition will collapse if we want to define heat at a state of a system. We cannot tell like this that, oh, there is heat in my, let's say, hot coffee. No, we cannot say like that. We will say instead there is thermal energy stored in that particular coffee. Yes, that is okay. But the heat can never be stored at a state. So we cannot define heat at a state of a system. For example, at this particular point, state 1, on this diagram, on the PV diagram, we cannot say that there is heat at this particular state. But we can tell like this that there is temperature. The temperature at this particular state 1 could be T1. It could be 100 or whatever it states. So these are what we call state properties. Okay, so or state phenomena. You understand me? So these are the state properties. But heat and work, they don't depend on the state of a system. They all depend on the part of the system. Means that if I want to transfer heat into this system, okay, so the magnitude of the heat will depend on the temperature difference. Higher temperature difference, higher Q. Lower temperature difference, lower Q. Similarly, if I want to transfer work into this particular system, so the work depends on the magnitude. If I transfer 10 kilowatt, so 10 kilowatt will be transferred into it. If I transfer 20 kilojoule, so it depends. You understand me? So whenever the piston is moving, then work is said to be done. So but if the piston is stationary, you cannot say, oh, there is work done on the system. Don't tell like this. So this is not good. Okay, so if we look into this diagram, we have two processes. Process B is given by this, whereas process A is given by this. Okay, so if we want to find the initial state at this particular state, the volume associated with the system is V1, and the volume associated with the system over here is V2. If you want to find the change in volume, the change in volume between state 1 and state 2, okay, for both processes, A and B, is going to be the same. You see, the change in volume is simply V2 minus V1 for A part, and this is for the B part. So it's going to be the same. You understand me? But if you want to find the work done when the system is going through state A up to state, through state A up to B, up to 2, the work done is given by WA. So the work done could be different from the work done through B. You understand me? So this shows that work indeed, we cannot define work at a state or at a point of a system, but we can only say that the work done from from state 1 to state 2 through B is this magnitude, and through A is also this magnitude. Okay, so normally the change in work is normally expressed through this function. Yes, so that's what I want you to know, and it is expressed as W12. You understand me? We cannot tell like this that this W12 equals to W2 minus W1. It's never done in thermodynamics in any way. You understand me? Because we cannot define W2 over here, neither can we define W1 over here. You understand? So, but we can define V1. V1 is clearly defined over here. V1 is 2, whereas V2 also is clearly defined over here. So we can find a change in volume through this state. Okay, so that all those parameters which depend on the root, okay, are what we call part functions. Okay, and those parameters which depend on only the two end states, such as temperature, volume, or whatever, these are called point functions. You understand? Okay, so now let's move again to shaft work. In shaft work, so let's say we have a shaft that is connected to a flywheel. Okay, so this is our flywheel over here. So the radius of the flywheel is R. Okay, so then we apply a tangential force, say F. So when we apply this tangential force, it is going to rotate the shaft. Okay, so now the torque applied on this flywheel equals to this particular tangential force times the perpendicular distance from the point of action. So you see, so this is a very primary elementary level mathematics definition. So the torque applied on a shaft equals to the force times the and then the perpendicular distance, which is the radius of the shaft. Okay, so then if I want to find a force, it is the same as torque divided by R. So now let us see if we want to determine the circumference of this particular flywheel. The circumference is given by this. So just 1 minute. Yes, so here we have, you see, if we have a circle like this, the circumference of a circle is nothing, it is 2 pi r. 2 pi r. This is called this is the circumference. Circumference means the distance, this distance is given by 2 pi r. Now, if we rotate this flywheel through 1 revolution, so then it means that we would have covered 1 circumference. If we rotate it to another revolution, so then the number of revolution is going to be twice. You understand? So the more revolution the the flywheel goes, then the higher the circumference, the total distance covered, okay, will become. So we will represent this number of revolution by n, small n. Okay, so small n is the number of revolution. So if n equals to 1, so it means we'll move only through 1 circle, 1 period, like this. So if n equals to 2, it means we cover only 2 distance. You understand? So now the work done is equals to force times distance covered. So the force is the perpendicular, this is the force, okay, or the force applied on the shaft times the distance. What is the distance? The distance is the total circumference, or the number of revolutions of the shaft, and which is given by, so wherever we see F over here, we represent by T divided by R, and then times S. S is the total distance. So total distance is represented by 2 pi R times N, which gives eventually this equation. You understand me? Okay. So now, if we want to express the power, the work in terms of power, the unit, be careful, the unit of this is kilojoules. So now, if you want to express in terms of power, what is power? Power is the rate of doing work. You understand me? So it means that we're going to have this W for the shaft. Okay. So the W for the shaft, the power is going to be the rate of doing work. So it is going to be the W shaft divided by time. You understand me? So it means that if we divide the whole of this function by time, we divide the whole of this function by time, okay, by t. The time is going to does not affect the torque. Torque is a constant term, okay. Neither is it going to affect the pi. It is going to affect only the n, the number of revolutions, the number of revolutions per second. So this is what we have over here. So eventually, whenever you see this equation, so this is the work done by the shaft in terms of power, which is in kilowatt. You understand? And the application of this is in the marine industry. Okay, so the marine industry, they normally have a very large shaft, which is necessary to propel the ship in whichever direction it wants to go. Okay, so unfortunately, I will not be able to give you break because some of you would like to save your data maybe for the next class. So I would like to move quickly, maybe for about half an hour again, then we will stop. Okay, so try to bear with me in this way. So now here we have electrical work transfer. So By definition, the electrical energy equals to the the voltage or the potential difference, which is V over here, times N. N is the number of electrons. The number of electrons is given by this, which is, its units is in coulombs. Okay, so coulombs. So now the electrical power can be defined as voltage times current. What is this current? How this came into the equation suddenly? The thing is like this. Current is the rate of flow of electrons. So it is N divided by time. You understand me? So current is all the time. It is the rate of flow of electrons. So wherever, if we divide this by T, we divide this by time. So then it means that the time is going to affect the N only. So that's why we change this to I. Okay, so then we could also express it in terms of this. If you want to find the electrical energy, okay, integrating from time T1 up to T2, we could have V times D times dt. You understand me? So, and again, it could also be expressed in this function, where this delta T is this. Okay, so now electrical power is the voltage times the current, as we all know. And this could also be expressed in terms of the current square times the resistance. The resistance of what? Of this cable. Or it could be expressed in terms of this as well. Now, the various units for the individual terms are: voltage is in kilovolt, current is in ampere, and then time is in seconds. So then we have, again, electrical work versus heat transfer. Okay, so in this particular situation, electrical work, the difference between electrical work and heat transfer, we will discover over here. Okay, let's focus our attention over here. We have a rod which is immersed into this particular closed system. Okay, so this could be a form of electric oven, and then there is air surrounding it, or sorry, inside the oven. Okay, so, and as far as heater is, or the heat transfer is concerned, there will be current flowing into this particular heater, and then consequently heat energy will be produced, which will be transferred to the air in this situation. So the total boundary, the boundary of the system, is given by this. Total boundary of the system is given by this. So the total boundary of the system consists of the electrical work and at the same time the heat transfer to the system. But over here, if we look here for the diagram below, here we have the heater, which is largely separated from the boundaries of the oven. Okay, so it's like you put the electrical heater outside. So we can have a situation like this, that this is our boundary. Okay, so the boundary of the system is given by this. So the heater in this case is outside the boundary of the system. Okay, so for this reason, we say that the main distinguish between electric work and heat transfer process is the selection of the boundary. An example, let us consider a well-insulated electrical oven, okay, being heated through its heating elements, the figure below. So the system includes the entire oven in there, including the heater. Okay, so for this particular one, consists of the entire oven and then the heater. However, the energy transfer to the oven is not caused by temperature difference between the oven and then the air. Instead, it is caused by electrical energy crossing the system boundary, and thus this is a work transfer. Yes, so it's a work transfer. So you see here there is current flowing into the heater that crosses the boundary of the system. So this is called work, let's see over here, work transfer process. So electrical work transfer. Whereas over here, we have heat transfer. So here we have electrical work transfer because of the fact that current flows and crosses the boundary. But here, even though the heater, again, is in the neighborhood of the oven, it has no direct interaction. So the current that flows through the heater has no influence on the oven. You understand me? So instead, there will be thermal energy transfer from the heater to the oven in this way. And this phenomena is called the heat transfer process. Okay, so again, we look at, so we have about 12 or 15 minutes more, then we will stop. 5:30, we'll stop, and then we'll continue next week, inshallah. So this is what we call the spring work. So spring work, I've told you, is the energy stored in the spring. Okay, so let's say when the length of the spring changes by differential amount, let's say the x. So consider this particular slab in which we have a spring at rest position in this way. So if you pull the spring downwards through a force F, so then it will be displaced through a distance dx. So the work done by the spring equals to the force applied on the spring times the distance. You understand me? So for a linear elastic spring, the displacement x is always proportional to the force applied to it. Okay, so for a linear spring, the force is always proportional to the displacement, which means x. If we remove this proportionality sign, we'll put a constant, and we name that constant k. You understand me? So that's what called the spring constant. Okay, so now substituting and integrating this equation, again, this gives us yes. So for this particular equation, let's consider this example. So we have a spring which initially it is at this particular state, and we are applying a certain amount of force, say F1, and it is being displaced by through a distance, say x1, and then similarly a different load is applied to another spring through a distance this. Okay, so and then it is being displaced by a distance x2, which equals to 2 millimeters. So now the spring work for these two springs gives us half of the spring constant. Okay, so we could use this equation. Okay, so it will be half of this spring constant times x2 square minus x1 square. You understand me? So this is a general phenomena, or the general equation used for this, where x1 is the initial and final displacement, okay, of the spring. So and again, I'll look for an environment where I will handle this particular question, and let me see where I have to stop. I have a certain portion which I have targeted. Okay, so wait. Okay, so let me see. 68. Yes, I think we will have to stop over here. Then next week we will start with types of boundary. Okay, moving boundary. Okay, so here, oh, sorry, I'm very sorry. Wait. No, it is not this. Yes, so next week we will start with this. So let me complete the few slides that are remaining. Let me finish with this first. Okay, so in this particular slide, we have a moving boundary. So what is moving boundary? Moving boundary means that we have a piston which is moving relatively to the cylinder. Okay, now the work applied on a moving on the piston is given by the force times the displacement. So initially, let's say the piston is at this position, and then it is being forced to move upwards through a distance delta x, and the force applied on this piston is given by F. So the work done by the piston equals to the force times the distance or the displacement. Now, what is this force? Force is there, and the pressure applied on this piston. The pressure applied on this piston is given by the force per unit area. So P equals to force divided by area. So it means that if I want to determine the force, force will be equal to pressure times the area times the displacement. So now area times displacement equals to volume. You understand me? So this is called PDV work. So the boundary work associated with any moving surface, such as a piston cylinder, this is what we refer to as boundary work. Okay, so if you want to find that, so this the work done from to this particular distance is too small, a very small distance. However, if you want to find the total work, the total boundary work from, let's say, state 1 up to state 2, then we need to integrate in this way. Okay, so now we have another form of a moving boundary work. Okay, and another equation that is associated with the moving boundary work can be estimated using this particular equation. Okay, so if we consider this particular graph, a fluid is being expanded in the piston from state 1 to state 2. If we take a very small infinitesimal area, okay, that's the area covered, or a small distance traveled by the piston, which is dA, and this dA is nothing, it is given by the P times dV. Okay, so this is the force or the work done by the piston in moving through a very, very, very small distance. Okay, so and the area under this particular curve, this small area, delta A, is given by this, and this delta A is the same as integrating from state 1 up to state 2 of PDV. You understand me? So now during actual expansion and compression processes of an ideal gas or ideal processes, the pressure and then the volume of the process path often is related to PV raised to the power n equals to a constant, or known as a polytropic process. So later on next week, we're going to look at the boundary work for a polytropic process, okay, for adiabatic process, for isentropic process, and so on and so forth. Okay, so I will stop over here. Next week, when we will meet, we'll be discussing different types of moving boundary. You understand me? So we have boundary because of volume, boundary due to pressure, boundary due to temperature, and then boundary due to adiabatic and polytropic. So these are areas we're going to cover next week. So I will stop over here. Now, if you have any question, we can discuss now. If there is any question, please let us discuss now. Yes, is there any question so far? Please, we can discuss now. Any question bothering you, you have problem with internet or whatever it is, or with the lecture, following the lecture or something like this, you can tell me. Okay, so then we can discuss immediately. Okay, so if there is no question, then again I will give a short sermon, okay, a very short tazkira, okay, our nasihat for our as we stay at our village. Okay, so